This summer, I investigated the coupling of single gold nanoparticles into polymer-based photonic structures with Dr. Lai and his group at ENS Cachan. Our work aimed at developing a simple, low-cost way to develop photonic crystals with defects. These are basically nanostructures that can manipulate photons for biological imaging, solar cells, and many other uses. Specifically, we used a direct laser writing, or DLW technique, to couple single gold nanoparticles to a negative photoresist structure. DLW works by using an objective lens to focus a laser beam on a small voxel in the photoresist film. The high laser intensity at the focusing spot causes the monomers in the photoresist to link and polymerize there, leaving a structure that can be uncovered when the monomers wash away during film development. The two go-to DLW techniques are 1 and 2 photon absorption, which operate at the high and of zero absorption regions of the photoresist respectively. Neither is perfect, as OPA is only good for 2D fabrication, and TPA is expensive and high maintenance. That's why our group answered by developing a new technique called low 1 photon absorption, which operates in the low absorption region with a moderate laser for 3D fabrication. To fabricate our nanostructures with LOPA DLW, we first cover a glass substrate with gold nanoparticles sandwiched by 2 photoresist layers, each a micrometer thick. Then we illuminate the sample at low power and use the nanoparticles' fluorescence signal to locate their positions. Once we know where they are, we crank up the laser power and fabricate micropillars around them using DLW. We then develop each sample in solution to wash away the monomers, and the result is a sample of nanostructures to analyze. During fabrication, the photoresist forms a microsphere around the nanoparticle. This coupling effect causes the nanoparticle's fluorescence to increase up to 15 times what it was before fabrication on average. We tested nanoparticles with 10, 30, 50, 80, and 100 nanometer diameters this summer, and found that the gain in fluorescence reached a minimum at 50 nanometers. We also noticed an upward trend between the size of the microsphere formed and the peak fluorescence. For future work, more data should be collected to confirm these results and make precise conclusions. Thanks again to Dr. Lai, my graduate mentor Chang, and everyone else who made this possible.